Thursday. We have a big and exciting class today. This is the attendance register. Any questions about anything? Before we start, any questions all that people already have? Nobody has any questions at all? I know that some of you do have questions that you're just too afraid to ask. You're a little bit spoiled because you just think, oh, I don't have to ask anything. Bob's just going to read my mind and answer my questions for me. That's how involved we've become. So the deadline of assignment 2 has been extended for the second time. I talked to Monica Seisenberger. Wasn't my decision. Monica Seisenberger's decision. So some third year students asked Monica if it could be extended for a second time. Actually, they didn't tell Monica it already was extended once. That's the bit they left off.
Let's go to Monica again.
So it's extended until Tuesday at noon. That means that there will be one more lab, and then that will be the last lab. And I have to tell Richard Roberts that as well, so he can show up. I updated assignment 3. So assignment 3 is on Blackboard. I wasn't going to print it out because most students will not do it. So I thought I would save paper. If you would like me to print one out for you, just let me know and I can print one out for you. You can have a look at assignment 3 on Blackboard and decide if you'd like to do it or not. Assignment 3 is very special, as all of the assignments are. It is the easiest assignment of the 3. I think maybe. And it's very unusual, this assignment. It's very unusual. You will not see an assignment like this anywhere else in the bachelor's degree program or the master's degree program.
None of your assignments.
It has a special video tutorial. So you can sit back, drink your tea, and watch the special video tutorial of how to do it on YouTube. That is raising the standard of educational excellence, I would say. Like, that is an unusual educational offering. I've never had such an offering before. And I attended 4 universities, I think. Yeah, 4 universities in 3 different countries. And I never had such an offering. So, yeah, very special. Any questions? So, did I answer all the questions just by my mind reading exercises? This is what we're going to talk about today, kind of. We're talking about an automatic streamline seeding algorithm. It's not this one exactly. This is the surface-based version of the algorithm, which is a little bit more complicated than the 2D version of the algorithm. We're going to talk about the 2D version of the algorithm today. This is that algorithm extended to surfaces, which a Swansea University student did. So a Swansea University student implemented this. It's a very gifted Swansea University student, I might add. Very talented. And for him, this was easy. It wasn't that difficult, actually. It's not a very difficult algorithm. But for him, like, I think he just used one hand to implement this. Yeah. You can find a copy of that on the DataBiz YouTube channel, by the way, that video. So we talked, this is all part of the same lecture. We talked about FlowVis with arrows 2 lectures ago, actually. And we started talking about integration with streamlines 2 lectures ago. And then last time we started to talk about the more accurate streamline computations. And then we started to talk about streamlines, flow visualization with streamlines, now that we know how to compute them. And we mentioned, or we talked about the definition of pathlines and streaklines. I thought of another analogy, by the way. Maybe one that's even better than the last analogy I gave. Does anybody remember the last analogy I gave with the popcorn and the river? The other analogy I thought of was with air balloons, helium air balloons. You don't have to inhale the helium to understand pathlines and streaklines. But a pathline, imagine you have one helium balloon, as one does at the carnival, and then obviously you let it go by accident, right? And then it flies off. The curve that balloon traces, if it was to trace a curve through the sky, that's a pathline. Now, if you had 100 helium balloons in a big bunch, and you stood still, and you released one balloon every second, and then you connected the balloons in the air with a curve, that's a streak line. And you can, if you think hard, you'll see that the path line is not the same as the streak line, because the path line is only created by one single balloon as it traverses the sky. Whereas a streak line is the whole collection, right? They're both going to be curvy, you know, they might even look similar, but they won't be the same, right? Yeah, in the streak line case, it's the curved line is only the first balloon, the path of the first balloon. Yeah, so that's another analogy. This also corresponds to injection of dye in liquid and smoking a cigarette. If you smoke a cigarette, then the smoke will emanate curves, and those are analogous to streak lines. And we talked about illuminated streamlines a little bit. And now we're talking about streamline placements. And we said last time that the default way to place streamlines is using your mouse, clicking on a point position in space, and then saying, see the streamline here, forward integrated, backward integrated. And if you see using an algorithm, which is kind of nice, right? Because it's not very much fun to sit and point and click with a mouse all the time. You can use a regularly spaced grid, but if you use a regularly spaced grid, you end up with a visualization that looks like this, with lots of overlapping streamlines, right? So redundant, thank you, Andy. Redundant computations, and not to mention it doesn't look nice, right? It's a funny topic, the idea of aesthetics and visualization, but actually it makes a lot of sense. We don't want to create a visualization that's painful to look at. I actually get a small amount of pain. That's not a good idea to create pain. Add pain with visualization. So it's good to make also an aesthetically appealing visualization that creates pleasure. So the question is, how can we do this automatically? That's the question. And we're going to find out the answer right now. It's an exciting answer, I can tell you that. So the overview of it's called an evenly spaced streamline seeding algorithm. The idea is that the streamlines should not lie too close to one another, as in this case, right? They're very close to one another. So basically the idea is if you want that the streamlines don't collide, you have to add some sort of intelligence to the streamlines that say, oh, I know. They have to be able to communicate with each other somehow, to be aware of each other. In this case, they're not aware of each other. They're just colliding. And here, some intelligence has been added to them that makes them aware of one another so they don't collide. So we choose a random seed point, and it's always a distance away from an already existing streamline. That's the key element, and that's the intelligence that we're adding to each streamline. Then we integrate forward and backwards until we approach another streamline, right? We don't want to collide with other streamlines. So we have a separating distance that we start with away from existing streamlines, and we have another separating distance or a testing distance that prevents us from colliding with other streamlines or overlapping. So the start position is controlled, and the end position is controlled or tested. So this is what the algorithm looks like in pseudocode style. So we compute an initial streamline. If the 2D domain is blank, then it doesn't matter. So we compute an initial random streamline, and we add it to a queue data structure, right, which is just a list of streamlines to be processed. Then we start our algorithm. We take the initial streamline and start the algorithm, and it's a big loop, right, a while loop until it's finished. Finished means the whole space is filled with streamlines. That's what finished means in this case. So we test, given an existing streamline, we look along both sides of the streamline for empty space for new streamline seeds. And we look at the empty space, a special subset of the empty space, that's a distance of d sep away, so some small distance away from the streamline. And if we find an empty space, we seed a new streamline. So if we find a space, we seed the streamline and compute it, start tracing it, and then add it to the queue, the same queue that's here, to be processed in the next iteration of the loop. And that happens, that process continues until all the streamlines have been taken out of the queue and processed. And when we finished searching the space for empty spaces along the current streamline, we finished that search and we finished seeding new points, then that streamline is called processed. We mark it as processed, and it's taken out of the queue, right? And then we take the next streamline in the queue and run the same process. Right, so here's a picture of that. I will do that. I will explain the same thing, but using a picture or using a visualization, which makes it much clearer. It's a good example of why we use visualization, right? It's much easier to understand with pictures than it is with words. So imagine we have no streamlines. We start with a blank slate, and we seed a random streamline in the very beginning. And let's say it's this dark one in the middle. So we choose a random seed. We integrate forwards and backwards until we have a streamline, right? And then we add it to the so-called queue for processing. We start at the one end of the streamline, right? This is the queue, the one in the queue. And then we start searching, like looking on one side, looking on the other side of the streamline for empty space. If we find empty space, then we seed a new streamline. And there it is. We found an empty space, we seed a new streamline. Then we integrate forward and backwards. So we have a new streamline. And we put this streamline into the queue. And then we return to the original. We were searching along this first one. And we're searching from the left to the right on both sides to find an empty space where we can seed new streamlines. So we continue our search. We find, oh, there's another streamline. There's another empty space. So let's seed a streamline there. And we integrate in both directions, the first direction and the second direction, until we have another streamline. And this third streamline is then added to the queue data structure. We continue our search. We've been searching. We get to here and we find an empty space here. So we seed another streamline. We integrate in both directions, this direction and this direction, and add it to the queue. And keep searching. So we search until we found a white space. This diagram could be a little bit, it's not perfect. For example, we could have seeded here, but for illustrative purposes, it works fine. So we find an empty space here. Then we integrate in both directions and add this streamline to the queue until we process the entire length of this streamline. When we process the entire length, what does that mean? When we search both sides of the streamline for empty spaces to seed streamline points, we're finished with this streamline. We've searched the space on both sides. We're finished with it. It gets taken out of the queue as being processed, and then we start with the next one. So in this case, the next one would be this one, because this is the first one we computed and added to the queue after the initial one. Does that make any sense? So in some ways, it's a big search process. What is it a search for? It's searching for two things: empty space and existing streamlines. And the search is not like top left scan line oriented. That's not how we're searching this space. We're searching this space on a streamline oriented basis. Taking a streamline, searching, taking the next streamline, searching, taking the next streamline and searching, right? So it's like a streamline oriented searching of space. That's another way to think about it. Does that make sense? Looks like fun, doesn't it? And then the question is, when do we stop? So you'll notice that these streamlines have ends, right? They end sometimes at some point. Well, how do we determine when we should stop a streamline, stop the integration process? Luckily, we have a slide just for that knowledge. So how do we know when to stop streamline integration? When the distance to a neighboring streamline becomes less than a certain threshold called detest. That's one of the conditions. So if I'm searching this space and I'm forward integrating and backward integrating, this test fails. Look, we integrate a certain distance and we're searching the space, and the distance to our neighbor has gotten too close. It's below the detest threshold, so we terminate it so it doesn't crash into our neighbors. Right? That's one of the conditions for stopping the integration process, the D tests. If the streamline leaves the domain, right? So if we're integrating and then we slip outside the domain, we stop integrating. When a streamline runs into a fixed point, we saw that last time. Does anybody remember Tony's video from last time? Tony McLaughlin's streamline integration video. It showed the integration process and then all the streamlines were being terminated in the lower right. That was running into something called a fixed point. And that's where the velocity approximates 0 value. That's also called a sink or a source, sink. When a streamline collides with itself, that can happen or gets too near to itself. There's no example of that in this slide, but it could happen that a streamline spirals and gets close to itself, like we saw in the integration example of streamlines being integrated in ellipses. And we just have a maximal number of steps. So we set an arbitrary number of maximum steps that prevent the streamlines from going too long. Maybe they get stuck in kind of a spiral pattern or some very, very long pattern. So we terminate them after an arbitrary amount of steps. Any questions so far? The energy is overwhelming here today. Really shocked. So this is, you can give the user interactive control over the separating distance between streamlines. So this is when you set the control to 6% of the domain or the image space. So this distance is 6% of the image space. So they're kind of far apart. And this is when you decrease it to 3%, it gets more dense, and this is down to, this is actually 1%. Someone stole the 1 off this slide, and they never gave it back. So you can, and you saw that in the video that we just played before, the user sliding the density control. So we could interactively control the density. Now, D-test, that collision parameter, is not exactly the same as D-separation. Usually it's half of D-sep. So that's the distance that we check to make sure we don't collide with other streamlines to terminate. Right? If D-test is roughly the same as D-sep, that's when they're roughly the same, like 90%. We get shorter streamlines. They're a little bit shorter, but the spacing is more even in this version. Here, D-test is a half of D-sep, right, 50%, and we get longer streamlines, right? They're longer, generally the average length, but they come a little bit closer together at the ends, right? So they're not as evenly spaced. So it's a trade-off between sort of the evenly spaced property and short streamlines or less evenly spaced but longer, more visually coherent streamlines. We can enhance those streamlines with some additional information. For example, we could change the thickness of the streamlines, right? That's called tapering. So here, it's not that easy to see, but the streamlines are thicker in their center and they get thinner towards the ends, and that's called tapering. That's an artistic effect. It's not as clear here as it is in the video that we just saw before. We can add glyphs that show the downstream direction, so now with these arrow glyphs, we can see that this is the downstream direction, right? The flow is pointing that way. And same here, this is a sink. right? Because the flow is spiraling inward there. And there's a paper that summarizes this algorithm in more detail, and there's a copy of it on Blackboard. It's called Creating Evenly Spaced Streamlines of Arbitrary Density. Any questions about that? And there's a video that shows the surface version. Here's a question for this extremely loud, rambunctious audience. What would be a good reason to have an evenly spaced streamline algorithm? Are there any good reasons to have such an algorithm? That would be a good test question, wouldn't it? Like, why? Why is that useful? Anybody feeling ambitious today? I'm going to call on somebody. If there are no volunteers. You're all supposed to do this. It doesn't matter because I'm not going to be looking at you. I'm just going to be looking at the names here. Oh, I know who that is, so I'm not going to call. I like to call on people sometimes, and then if I don't know exactly who they are. That's fun. Some interesting names on here. How about Daniel Barreto? Did I say that correctly? Daniel, what do you think? Is there any reason we might have such an interesting algorithm? Are there any advantages to having that, or are there? I'm basically asking, why do we even talk about this?
Makes it easier to look at. It's not too complex. They can work out what's going on with visualization.
That is very close to very correct. So if we have an algorithm like this that generates streamlines on the flow, it makes sure that we capture all the characteristics of the flow, basically. So we capture all the features, like the sinks and the saddles. That's a sink, that's an area of swirling motion. This is a saddle, by the way, so it has this 4 hyperbola. It just makes sure we capture all the characteristics of the flow. If we were to try to see the streamlines manually, we might miss some features, right? And it reduces the redundant computation of that other grid-based strategy, right? So those are two very good reasons to have it, to have such an algorithm. Okay, good. So we're done with that one. Let's move on to the next one. I wonder if I have any videos to show. Oh yeah, let's have a preview. So we talked about streamlines. We talked about pathlines. We talked about streaklines, and we talked about glyphs. So when you think about vector glyphs, they're based on points, right? You position a glyph at a certain point in space. You could also call it the dimensionality of a point. Does anybody remember the dimensionality of a point? That's a good question that you guys know the answer to.
0.
0. Points are 0D, right? 0 dimensionality. They have no length, no width, no height, no depth. They're kind of theoretical. I mean, in some ways. Did anybody take geometry in high school? Does anybody remember like one of the very first statements that all Euclidean geometry is based on? The assumptions that are made for Euclidean geometry, like if you want Euclidean geometry to work and be correct, you have to assume the following. And there are like 3 assumptions that all Euclidean geometry has to sort of believe as true. Like the existence of points, like you have to believe, you have to assume that points exist. That's one of the basic assumptions behind Euclid. It's not provable, right? When I took geometry in high school, it was all proofs, right? You prove things like the area of a triangle is half of its height, square divided by 2. And you prove that it's true, right? You do all these proofs, but all the proofs rely on a few basic assumptions. One is that points exist even though they don't occupy any space. It's kind of a contradiction. And you have to assume that lines or edges exist too, right? Because they don't occupy any. They have a length but no width. And you have to assume that surfaces exist too, even though they have no width. So I'm digressing. I don't know why. Oh, now I remember why I started to talk about that. So we have glyphs that are based on 0D points or positions in space. Then we have curves, which are streamlines, for example, based on one-dimensional curves, right? Or lines. So we're increasing the dimensionality now to 2 dimensions, or 2.5D surfaces. So now we're talking not about points, not about lines, but we're talking about surfaces. So we're raising the dimensionality. And we're going to talk about something called stream surfaces. Does anybody remember what a streamline is? That's another good question. I can see that the brain activity is somehow slowed down today. Yes, there are multiple ways to express the definition of a streamline. You just express it. The path that a massless particle would take if it was dropped into the flow. That's one definition. That's correct, by the way. Another definition is a curve that's always tangent to the vector field. And could anybody imagine extending that to surfaces? The suspense is agonizing, isn't it? So a
surface which is tangent to the vector field.
Bam! Yes! Well done. So a stream surface is a surface that's always tangent to the vector field. Yeah. And you could think of it also as a massless surface that when dropped into steady state flow is always tangent to the flow. That's one way to possibly think about it. So these are stream surfaces, right? And so their surface is always tangent to the flow, right? And they have some advantages over streamlines. So this is a surface. This surface is a little bit special because it's not made out of triangles, but it's made out of quad patches instead of triangles, right? And surfaces give some advantages because we can add special rendering options to surfaces that we can't with streamlines. So we can texture map surfaces more easily. We can add shading information to surfaces more easily than lines. Surfaces are more visually coherent, especially for the 3D flow case. When you try to seed streamlines in 3D, sometimes it gets very complicated. visually. It's hard to see what's happening. Stream surfaces also have this property that they partition the flow into different areas of behavior. So the flow on one side of the stream surface behaves differently than the flow on the other side. And these are showing stream surfaces in action, so to speak. So the user has generated some stream surfaces and now they're displaying them with different rendering options. These are texture map stream surfaces, and they've been texture mapped with arrows. So those arrows are just animated in the direction of the downstream direction of the flow. Right? And you can use different kinds of textures to add different kinds of effects. And you can recreate evenly spaced streamlines with these stream surfaces as well. This kind of stream surface. So that's the mesh, by the way. That's a close-up of the mesh that the stream surface is based on. These are so-called timelines. Does anybody know what a timeline is? You see, if I tell you, oh, these are timelines, what do you think a timeline is? Given that animation. Pop quiz. Anybody want to guess what a timeline is?
Shows how something is progressing through time.
That's true. That's true. Lots of things do show us how things are progressing over time. Anybody want to take a guess at a more precise definition? I'm going to call on somebody because the energy level is just overwhelming in here. I need to quiet it down. Okay, how about Dougal Stein? Is Dougal here? He signed the register. Back there, hiding. Dougal, what do you think a timeline is? You've seen them. What do you think they are? That's what they look like. Any idea? Don't want to take a guess? Does anybody want to help out Dougal? I see that the team spirit is overwhelming. I guess it is a difficult question, but definitely be prepared to answer that for the test.
Is it just like the streaklines?
It has something in common with those other lines, doesn't it? Streamlines, streaklines, pathlines, there's something in common, right? So a streamline is you drop a single point into the flow and watch the curve that it traces out. Well, now you're not dropping a point into the flow, you're dropping a curve into the flow and watching the path that the curve traces out through the flow. That's a timeline. So this is the seeding curve. In each one of these is a curve, right? And it's always tangent to the flow. So it's a curve that's dropped into the flow or seeded, and then it's released into the flow, and it's always tangent to the flow, right? So back to the balloon example, the balloon analogy. If I had a balloon, a single balloon, and I had 5 imaginary friends. I had 5 friends, and we were all holding a balloon, like one standing here, one standing here, one standing here, and one standing here. And we all released the helium balloons at the exact same time, timeline, and then connected them with a string or a curve. That would be a timeline. Right? So it's a number of points connected by a curve, all released into the flow at the same time. Right? That's a timeline. And you can create timelines like this very easily with the algorithm we're going to talk about. And you can extend them to so-called time ribbons, which are ribbons that are seeded, ribbons that seeded at the same time and are released into the flow. But ribbons have this advantage that they're thin surfaces, so they can be shaded. And when you add shading, it makes them easier to perceive in 3 dimensions, the depth information. And we can construct path surfaces. So path surfaces are surfaces that are everywhere tangent to the flow, but in the unsteady case. So unsteady flow. So that's what we're going to talk about. Looks exciting, doesn't it? Oh, we're also going to talk about some stream ribbons and some other things. So we talked about the vectors based on points, the curves based on lines, the streamlines based on curves. A stream ribbon, right, looks like this, and it's a surface with a fixed width that's always tangent to the vector field. So if I seed, for example, a streamline here and a streamline here, and I connect them with a surface, I can shade the surface. Now the streamlines will twist, and so they convey more information than a single streamline. They convey the rotational properties of the flow. So it will twist, and something has to be done to make sure that the stream ribbon does not diverge and get too big. So a special normalization is performed after each integration so that the distance between the streamlines remains fixed. So in some ways it's very similar to a stream surface. Stream surface, there's no restriction placed on the amount of divergence, so it shows the divergence of the flow. The stream ribbon lets us concentrate on the rotational properties of the flow. And these are stream ribbons, by the way, this red and green image ribbons that's showing the rotation. So we see, for example, there's lots of flow rotation here and almost none back here. And you wouldn't be able to see that with streamlines. Right. So the idea for stream ribbon generation is we start with a single point in 3D, right? And we add a second point in 2D, a special distance, a fixed distance away from the first point, right? We integrate from the first point, right? It's the same as a normal streamline integration. We integrate from the second point. It's the standard streamline integration again. So we have 2 streamlines that we're integrating. And then after each integration, a distance test is performed to see, okay, have we gotten further away from each other or closer to each other? If the distance has changed, we fix the distance. We normalize it back to its original. And that's the idea. So the distance between the first and second streamline is always the same. And we can render stream surfaces, right, with these different kinds of patterns, right? And I'll show some more examples next time of special rendering options that we can use on stream surfaces. We can add textures, right? That's a texture to a stream surface. That's also a texture. These are arrows, right, that show the downstream direction. I don't think I have those right. Oh, I do have them. Okay, let's look. So these are more stream surfaces, but with different rendering options. In this case, the surfaces have been texture mapped again with a gray scale noise texture, and then the texture is animated to show the downstream direction of the flow. You can see the stream surfaces do look different than ISO surfaces. They really, the way they look is different. These are the same data sets actually we've been looking at the whole semester for FlowVis. These are still the petrol and diesel engine simulation data sets. So this is the diesel engine simulation data set, and that's a stream surface inside the combustion chamber that we've already seen a few times, right? And we can see the axis of rotation inside the diesel engine combustion chamber, right? This reminds me of Lord of the Rings for some reason. It reminds me of one of the monsters in Lord of the Rings. I can't remember the name. Maybe the Balrog? I think that's what it is. I think it's called a Balrog. It's nicer than the Balrog. But like, this is a head. I see this a little bit like a head, and that's the body. And it's looking down at Gandalf on the bridge. But this came out. I'm pretty sure this. I think this came out before. No, maybe not. Maybe it was after. I can't remember. Anyways, it's an interesting flow visualization. And you see that this is more complicated. We're getting into a more advanced topic than aeroglyphs or streamlines. Starting to get complicated. And that's a stream surface through the cooling jacket. So that cooling jacket flow is very complicated. And here the two sides of the surface have been colored. So the red is one side of the surface and the green is the other side. So that helps to convey the twisting motion of the surface. So we'll have a preview and then we'll stop. So next time we're going to briefly talk about flow volumes in stream tubes. Right, and we're going to briefly describe their dimensionality, and then we're going to talk about how to construct these surfaces, how to come up with an algorithm that produces the surfaces. Right? And it's based on, just as a preview, it's based on quads that split. Yeah, under certain conditions. Okay, happy Thursday, everybody. Okay. Random. Random. Yeah, whatever you like. Yeah. Yeah. Or you could just choose the middle.
Just
that would
the
be
middle.
another possibility.
Okay.
Yeah.
Thank you.
Texture-based visualization. So it's just using textures to visualize the flow. So we used aeroglyphs. That's called direct flow visualization. We use streamlines. Those are based on curves. That's called geometric flow visualization. There are no textures involved. And then we can use textures to visualize the flow, like in that video we just saw. That was an example of a combination. So stream surfaces are geometric FlowVis, and textures are texture-based FlowVis. So that was actually combining the two together. Yeah, a little confusing. That's why I was mentioning, oh, this is starting to get a little bit more advanced. Yeah.
Thank you so much.
Sure.
With the Betty bits, I'm still struggling to pick out exactly what it is, and I think I've got to the point where I think I might be getting the reading in the data wrong. I mean, that's
Okay,
I've got just a quick picture of what I've got so far,
Yes, it looks
and it doesn't look.
looks a bit
Yeah.
noisy. Looks a bit noisy. So Betty is, it's this shape like an aquarium.
Yeah.
And you got the dimensionality correct?
Yeah.
Like you know that one side is longer
Yeah,
and then
yeah.
the second, so they're not. It's
It's
not
all
a
being
cube.
read in properly to parity, and so I've been trying to get subsections of the thresholds of the data to try and pick out or only things with below a certain magnitude go in or whatever. But I'm
Yeah.
still struggling to get.
Yes, something's gone wrong there.
Okay.
Something has gone wrong. It's the bottom half or the bottom plate of the aquarium has been heated,
Okay.
and the top is not.
Okay.
So when you heat the bottom, the flow starts to curl up, so to speak. So you're looking for a four-ish regions
Okay.
of curved flow,
Okay.
of like spiraling. It's not going to show up as a spiral unless you use streamlines. That's not part of the assignment, but it will just show up as four-ish regions.
Okay.
Special, but it's not as smooth as Sally.
Okay. Cheers. I'm gonna have a look
Yeah.
at it.
Can I submit that assignment too?
Yeah, you can. Yep. Looking forward to having a look at it. So the class was totally dead today, but suddenly everybody has questions. Yeah, you can give that to me.
Just one question about Sally. I've tried to use a smaller
Okay,
array,
good.
and it is less noisy and it's more smooth,
Mhm.
but it looks less of the turning the direction it has. So, and also how to be able to use a larger array so to get more information about from it, but also keep the smoothing of the.
Did you try visualizing Sally with glyphs?
I'm proud of the glyphs now.
I think that would be an interesting experiment to see what Sally looks like, your Sally looks like with glyphs.
Mm-hmm.
That would be interesting because you have, it's supposed to be smooth, so like imagine all the arrows pointing in the same direction,
Oh, okay.
but in a spirally pattern. So you have something going on where you have the pattern, but you have noise, like a jittering happening in there with your data too.
Okay.
So it's like you have two patterns. You have the Sally pattern, but you have a noise pattern added on to that that's causing the vectors to jitter somehow. And I don't know why.
And also in the Sally function, what is the time variable?
You can pick any time. By the way, one thing you might you showed me you were taking slices of the data.
Yeah, it was also taking slices.
Yeah, and I saw noise in the slices too.
Okay then.
So that means something is wrong. Something is wrong. I don't know what that extra added noise is.
Okay, what size size array do you expect for me to initialize Sally at first? Or is it any you decide size?
Like 64 cubed is a typical size for to visualize Sally, or 128 cubed. Maybe ask Richard Roberts what he thinks. The noise, but it's a bit. I'm a bit mystified, to be honest. A bit mystified. I haven't seen quite that thing that you showed me. I don't think I've ever seen that before.
Okay then.
Yeah.
Oh, then that's all. Okay.
Okay. Yep.
Thank you.
Yep.
There's a limit on the number of times you can use the same tool, also same program,
No, there isn't.
So
You
we
can
could
use the
use the
same
same
program for all the
as long as they're
visualizations. Yeah.
different enough.
They have to be two different visualizations for each data set.
Okay.
That's the requirement.
Right, thanks.
Good. Another question.
The vector and scalar conversion. don't know. Are you supposed to do that inside the programs?
Yes, that's right. That's right.
So if I'm using Vereen, I think it is.
Yep.
You drag and drop things onto the
Yep.
to the workspace.
Yep.
It's, so I have to make my own
Conversion.
Okay.
With Voreen, though, however, Voreen has some flow visualization features. So you can actually trace streamlines in Voreen. So that implies that they will accept vector data. So if you look carefully at the tutorials, the Voreen tutorials, and look up how they compute streamlines, you might be able to skip the conversion process and read in the data directly. Same thing with ParaView and all the other, well, not all the other programs, but ParaView can trace streamlines. So you might be able, if you look carefully, skip the conversion process into scalars and read the data directly. It's just a matter of figuring out how to do that. But in order to trace streamlines, you must have the original vector data. You can't do it from scalar. You can't do it from scalar data. Does that make sense? I would be interested. In fact, I wish I had made that part of the assignment to say, oh, you're allowed to use streamlines and not convert the data. Actually, that would have been. But I didn't realize I was going to get this far already, like with the streamlines.
Well, I tried the VTK software.
Yeah.
I just couldn't actually get it working.
Okay, yeah, VTK is complicated. So that again, you'd have to look at like on YouTube tutorials and stuff like that.
Yeah, I mean,
It's complicated.
I tried quite a lot of things.
ParaView is what students generally end up using. ParaView, yeah, I think that's the most popular one. VTK is not so popular.
So if I use Vereen, then I don't actually have to do any programming.
That could, well, you still have to save Sally into a file. So you'd have to add a method to Sally that saves the data into a file. But you can pass the assignment without any programming at all. You can get a pass. The question is, like, what, if you want to get all the points, you definitely have to add a method to Sally that stores the data in a file that can be read in by Voreen or whatever you choose to use.
Is Sally in a different format or something?
You make the format for Sally. So Sally, all it does is print out the data. It prints, well, it stores the data in an array. So you have to go through the array and do something, like print it out, save it to a file or something. You have to get it in the format from the array onto a disk that one of the pieces of software can read. So you could, if you can figure out how to read in the vectors directly, you can skip the conversion process.
Okay. And the third assignment, I noticed you have to ask to get a paper.
Correct. You want me to tell you a paper right now? Or you want me to email you a paper? Or?
Could you email?
Yeah, you have to send me one first though to ask.
Of course. Yeah. I'm really glad about the extension though.
Okay, good. Because you're not prepared.
Yes.
Okay, were you the one that asked for it?
No, I wasn't.
Okay.
I was actually going to ask you.